In this video, we will cover 5 Chapter 9 exercises. Question 1. Which reagent would accomplish the following transformation? So this is conversion of an alkene into cis-diol. Reagents that would do that are potassium permanganate under mild conditions or osmium tetroxide followed by suitable workup. So when we look at 4 choices here, choice A is actually permanganate under mild conditions, permanganate in basic solution and in an ice bath. So that looks right. B and C are 2 ozonization reactions, and ozone actually cleaves double bond, so product would have been an open chain compound. And D is an epoxidation reaction with peroxy acid, so product would have been an epoxide, 3-member ring with oxygen. So correct answer is A. Stability of the following carbocations from the least stable to the most stable is. So you look at these carbocations and you classify them. Least stable would be methyl cation. Which one is methyl cation? Well, that's C. That's the least stable. Then second least stable would be primary cation. So of the remaining A, B, D, is there any primary? Yeah, D is primary. And then next in the order of stability, in the order of increasing stability, is secondary. We have A and B left. Is any of them secondary? B is secondary. And the most stable is tertiary, that's A. So that's the order of stability, C, D, B, A. Question number 3, what is the structure of the reaction product? So we have addition of water to an alkene under acidic conditions. And this is the best to use pen and paper and write down the reaction. So we start with starting material, that's 3,3-dimethyl 1-pentene. And so first step is protonation to give the intermediate cation. It's secondary cation. Whenever there is secondary cation, check whether it can rearrange to tertiary. And I drew here 2 methyl groups, 3,3-dimethyl groups slightly differently, so it's easier to draw the arrows to show methyl shift. So methyl shift of one of the 3 methyl groups will result in formation of tertiary carbocation. And now that tertiary carbocation reacts with nucleophile, which is a molecule of water, to give intermediate oxonium ion, which loses proton to give the final product. So that's the product, and now we can compare product with choices that are offered, and we can see that product matches compound C. So that's correct answer, C. Question number 4, which alkene is the most stable? First, we look at the degree of substitution of an alkene, how many substituents there are on the double bond. And so A has 4 substituents. That's pretty stable. We can't have more than 4. And then B also has 4. So A and B have 4 substituents each. It can't get more stable than that. C, there are 3 substituents on double bond. That's less stable than A or B. And D, only 1 substituent on double bond. That's rather low stability. So it's either A or B. When we compare A and B, we can see now, since degree of substitution is the same, now we look at stereochemistry. So we can see when we compare them that A is trans, B is cis. Trans is in general more stable than cis because of the reduced steric hindrance. So in this case, correct answer is A, because it's both tetrasubstituted and trans. A compound with a molecular formula C12H16 reacts with 2 equivalents of bromine. How many rings does the molecule have? So here it's very important that it reacts with 2 equivalents of bromine, which means there are 2 pi bonds, because rings in general don't react with bromine. The only rings that would react are 3 and 4-membered rings, but if that was the case, that would have been specified in the question. So we start with molecular formula. We need to calculate the number of degrees of unsaturation. So degrees of unsaturation is 2 times number of carbons plus 2. That's 2 times 12 plus 2 minus number of hydrogens and halogens. In this case, we don't have halogens, but we have 16 hydrogens. So minus 16. Divided by 2, when we do the calculation, that's 5. That means total of 5 degrees of unsaturation. That means total of 5 rings and pi bonds. From the reaction with bromine, there is reaction with 2 equivalents of bromine. We know that there are 2 pi bonds, which means there are 3 rings in the molecule. This completes Chapter 9 exercises. There will be an additional video with more of the Chapter 8 and 9 exercises.